Welcome back, folks. Today we are deriving your favorite. Let me warn you guys, do not put chalk on your cowboy hats. And now the ground is a mess. But today we are deriving trigonometric identities. And I think there are 32 of them, depending on the title. And we'll go through some basic definitions and properties first. First off, cosecant is 1 over sine. Secant is 1 over cosine. Tan is sine over cosine. And cotangent is the reciprocal of tan. Over here in orange, we have what we call periodicity of these trig functions. Sine of x plus 2 pi k is just sine of x, where x is the angle and k is just any integer. The same goes for cosine. What does this mean? If we have some angle on this circle or ellipse or whatever it is, it should be a circle, and we go 2 pi, meaning 360 degrees, we'll return to the same place. This is because, any circle has 360 degrees. And the same goes for tan, except we have a pi and not a 2 pi. Over here in the pink, I like this pink, sine of negative x is negative sine of x, and cosine of negative x is just cosine of x. Cosine is an even function, sine is an odd function. Why? Well, any point on the unit circle is represented by cosine and sine, where cosine is the x-coordinate and sine is the y-coordinate. Well, when we reflect the x, when we multiply x by -1, we're changing the sign into a negative sign. But the cosine is conserved. It does not change. And the same goes for the second and third quadrants. Now, tangent is a quotient of an odd function and an even function, making it an odd function itself. And now we're going to be covering people's favorite, the Pythagorean identities. And of course, these come from the Pythagorean theorem, and if you're not familiar, I'm not sure what you're doing here, but you're welcome. A squared plus b squared is, of course, c squared. And this applies obviously to right triangles like this one on the unit circle without a circle because I couldn't draw it. But anyways, let's get to it. Firstly, I'd like to take the sine of this theta, and the sine of theta is opposite over hypotenuse, b over c. Cool. Now, the cosine of theta is adjacent over hypotenuse, so a over c. Very nice. Now we're going to use the Pythagorean theorem. And firstly, I'm going to divide both sides by c squared. So we're going to get a squared over c squared plus b squared over c squared. Well, this will all equal 1 because c squared over c squared is 1. And I'm going to take the square outside, meaning I'll just put parentheses, and same thing here. Why did I do that? Because now we can replace a over c and b over c with these. So a over c is cosine, of course squared, plus b over c is sine, again squared, equals 1. Now they're usually commuted, so you could flip them, it's fine. And well, that's it. That's all there is to it. Except you might be wondering, what about other quadrants? Well, it's no problem actually. If you have the angle, for example, over here, and it forms a theta. Now both of these have the same values, so sine and cosine here are equal to the sine and cosine here, except they're negative here and they're positive here. But that doesn't matter, since we're already squaring sine and cosine, so this applies to every quadrant. Now you might be wondering, what if we have the sine of 90 or the sine of 180? Well, that doesn't form a right triangle, does it? That's fine. You can maybe find an elegant proof out there, but I'll give you a very rough one right now. So if, for example, theta is 0, meaning we don't have a triangle, well, we're going to have sine square of theta plus cosine square of theta. Well, sine of 0, even sine squared of 0 is 0. Cosine of 0 is 1. This will give us a 1. So as you can see, it still holds even when theta is 0. And when theta is 90, the same thing will happen, where sine of 90 is 1, cosine of 90 is 0, and so we get a 1. Same thing with 180. All right. where sine is 0 and cosine is 1. And the same thing with theta equal 360 or 2 pi, but 2 pi is the same as 0 plus 2 pi, and we've already covered that. But wait, we're not done. We have two more identities that come from the Pythagorean identity, and these are used in integration, or at least I've seen them being used, and well, they're very simple to derive. So we have the one we just derived. Now what we can do is divide by cosine on both sides, except cosine has to be not equal to 0, just so it doesn't become undefined, but that's fine. So sine square of theta over cosine square of theta plus 1 is 1 over cosine, which we already know as secant. Sine over cosine is just tangent, plus 1 is secant square theta. And that is the second Pythagorean identity. And the third one is very similar to this. You take the thing we already had, but now we divide, as you guessed, by sine. We'll get a 1 plus a cotangent equal a cosecant. And so here, these are easy to memorize: cotan, cosecant, tan secant, and sine plus cosine, of course. And this is all that comes out of the Pythagorean identities. Very fundamental, very useful. Alright y'all, cofunction identities. They show up in the SAT. The cosine of theta is equal to the sine of 90 minus theta. Now you're not going to be deriving this in the middle of the test, but it's important to get an intuition for it. And here I've drawn the 10th or 12th unit circle, and this is the best one till now, so appreciate it. I'll erase it later. We have the common points 1, 0 and 0, 1. Of course, we have a different version where sine theta is equal to cosine 90 minus theta, but I don't want to waste space. Okay, how do we do this? Well, we're gonna construct a line with an angle theta. And we're gonna construct another line with an angle theta. But this one is 90 minus theta. We're starting at 90 degrees and we're going back theta. Very nice. Now the main argument here is that if I draw a chord from this point to this point, it will have the same distance as this chord. So what is this point? Well, this point is just the cosine of theta and the sine of theta. And this point is the cosine of 90 minus theta and the sine of 90 minus theta. How do we get the distance? If you remember, the distance formula says that d is equal to the square root of x2 minus x1 squared plus y2 minus y1 all squared. It's not very clear, but we're gonna put it to use right now. Okay, so for the first distance, I'll call it d1. We're gonna get d1 is equal to the square root. I'm gonna remove the square root by squaring both sides, so we'll have d1 squared is equal to x2 minus x1, meaning cosine theta minus 1. Cosine theta minus 1, of course, all squared, plus sine theta minus 0. Well, that's just sine theta squared. And very similarly, we'll have d sub 2 squared is equal to cosine 90 minus theta minus 0. Well, that's just cosine squared of 90 minus theta plus sine 90 minus theta minus 1 squared. So we're going to write that over here. Very nice. Now what I'm going to do is equate both of them as we just said, and I'm going to expand at the same time. Not me, the parenthesis. Okay, so cosine minus 1 squared, that'll be cosine squared theta minus 2 cosine theta plus 1. And that'll equal d2. Well, they're both squared, but that's fine. d2 being cosine squared 90 minus theta plus 2 sine, well, sine squared 90 minus theta plus 2 minus 2 sine 90 minus theta, and of course plus 1. So I'll rewrite and we'll see what cancels out and what we get. Okay, so previously we got cosine squared minus 2 cosine plus 1 plus sine squared is equal to cosine squared 90 minus theta plus sine squared 90 minus theta minus 2 sine minus theta plus 1, a mouthful. Anyways, so we get some simplification here. We have cosine squared plus sine squared, according to our Pythagorean identity, is 1. And we can add this 1 to this other one. We'll get 2 minus 2 cosine theta. On this side, we have something very similar, cosine squared 90 minus theta and sine squared with the same argument. We'll get a 1. We'll add it to this one. We get a 2 minus 2 sine 90 minus theta. Very nicely, we cancel the 2's. We divide by negative 2, and we'll get cosine of theta is equal to sine of 90 minus theta. And that's pretty much the derivation, except you might ask, last time we drew the angles both in the first quadrant. What if they're not in the first quadrant? That's fine. Constructing the same sort of lines, for example here and here, and this is for some larger angles, you can draw similar chords and you get the exact same thing. Now for some of these special cases where theta is equal to 0, 90, 180 or 270, we can cover them very quickly right now. We know if theta is equal to 0, then the cosine of theta will equal 1, which is equal to the sine of 90, which is equal to the sine of 90 minus theta. And this, as you see, still holds. And if theta were 90, cosine of theta would be 0, which is equivalent to, well, sine of 0. But sine of 0 is sine of 90 minus 90, but 90 is theta. And so we have the exact same thing. And if we have theta is equal to 180, well, cosine of theta would be negative 1. And this, we would have it equal negative sine of, well, 90. And since this is not function, we can transfer the negative sign inside the argument, and that will be sine of negative 90. But sine of negative 90 is precisely 90 minus theta, or 90 minus 180. And when theta is equal to 270, cosine theta will be 0, which equals sine of 180. But sine of 180 is equal to sine of negative 180. But sine of negative 180 is just sine of 90 minus theta, which is 270. And so this covers all the cases. 360 is just 0 with a period of 2 pi added, or 360. And that covers it for the cofunction identities. But wait, I just proved that cosine of theta is equal to sine of 90 minus theta. What about the other way around? Well, that's an easy fix. You can just name 90 minus theta h, and that means that theta will equal, well, 90 minus h. So replacing these, we'll get cosine of 90 minus h is equal to sine of h, and now we have it the other way. Since theta spans all the real numbers, h will also span all real numbers, and we have proven all cofunction identities. Well, all of them that include sine and cosine. Okay, now this is a big one. It uses the same technique we just used, but everything else will follow from it, every other identity. Well, almost. But this is the last identity that we'll have to use a graph for. And now the angle identities say that if we have sine of a plus b, we'll have sine of a cosine b plus sine of b cosine of a, and something similar for the difference identities too. So for this derivation, I'm going to draw another line because we love lines and chords. And this will be angle A. And I'll draw yet another one, and this will be angle B. And one more one. I'm doing great tonight. I'll have, that is curved, I'll have negative b. Now, what we're essentially doing here is measuring the distance between this point and this point, and this point and this point, right there. Again, they must be equal by our previous argument. Let's get some coordinates down. Here we have 1, 0. Here we have the sine of, well, the cosine of A and the sine of A. Here we have the cosine of A plus B and the sine of A plus B. And here we have the cosine of negative B, but cosine of a negative argument is just cosine of that positive argument. And sine of negative B, which is equal to negative sine of B. And there we go, we have all our coordinates down. All we need to do is calculate the distance like we did previously and equate them. Okay, so I have gone ahead and written them down. We have d1, which is this one right here, is equal to cosine A plus B minus 1 plus sine A plus B minus 0, of course, squared respectively. And d2, which is a bit more interesting, we have cosine A minus cosine B squared and sine A minus sine B, which makes it a plus sine B, all squared. Now I'll rewrite and expand and blow up. Okay, finally, after expanding and rearranging some things, we get this big boy. Great guy, big man. So we have cosine square A plus B plus sine square A plus B plus 1 minus 2 cosine A plus B equal cosine square A, sine square A, cosine square B, sine square B minus 2 cosine A cosine B plus 2 sine A sine B. Again, double mouthful. So let's simplify by observation right here. We have these two will add up to 1 according to our Pythagorean identity. So this and this will both be 1. 1 plus 1, that'll be a 2. So we can cancel this and that. So it'll be 2 minus 2 cosine A plus B. We have cosine square of A plus sine square A. These will be 1. These will also be 1. Plus we'll get a 2. So cancel. And so we'll get 2, well, this is equal. 2 minus 2 cosine A plus 2 sine A sine B. Okay, let's write this down. So 2 minus 2 cosine A plus B is equal to 2 minus 2 cosine A cosine B, well, plus sine A, well, 2 sine A sine B. Alright, very nice. First, we'll cancel these two 2's, and then we'll divide by negative 2. We'll get rid of this, rid of this, but since we have a plus sign, we'll have a minus sign. So cosine of A plus B will equal cosine of A, cosine of B, minus sine of A, sine of B. And there we go. We have the angle addition identity for cosine, and everything else will follow from this. Okay, so previously we got this result. This will carry everything else. Now we want to prove the angle subtraction identity, or it's still sort of addition, but we're adding a negative number. So we'll have cosine of A minus B, but I'll rewrite it like this: cosine of A plus negative B. And this is so we can use this up here. We'll have the cosine of A and the cosine of negative B, but the cosine of negative angle is just the positive angle. We'll have minus sine A and sine negative B. But since it's an odd function, we can take the negative outside. It will be positive, and this will change into a positive. So that will be plus sine A sine B. And that's the second identity. Now we want the sine identity, or the angle addition sine identities. Now we're going to use the cofunction identity, something we proved earlier. We'll have sine of A plus B. That will equal cosine of 90 minus the same angle. There we go. And now we're going to group these in a way that will help us. And that will be cosine of 90. We're going to distribute the minus signs, minus A, minus B. We're going to get minus A, and then minus B. There we go. And so now we use what we learned before. that cosine of a plus minus b, or now we can rewrite it as cosine of a minus b is equal to this result right here. So we'll have cosine of a, which is cosine of 90 minus a in this case, cosine of b, cosine of b minus the sine of a, the sine of 90 minus a, and the sine of b. Of course, this will be a plus sign. Very nice. Now we know that cosine of 90 minus a must be sine of a, according to the cofunction identity. Once again, this will stay the same, plus this will be cosine of a and the sine of b. And there we go. We have the sine of a plus b is equal to the sine of a cosine b plus cosine a sine b. Okay, so now we have this result and we can prove the difference identity. That'll be sine of a minus b, and this will be just as easy as this one. We'll have the sine of a and the cosine of negative b, but once again we can just write it as positive, plus the sine of negative b and the cosine of a. We can take the negative out, as we said, and there we go. We have the sine of a minus b equals sine a cosine b minus sine b cosine a, and that covers all the angle addition identities. We are nearly there. We have just 4 more chunks to go, but they're easy. They follow directly from what we said before, from what we derived before, and these need no graphs, which will be much easier for me because I keep drawing random ellipses. I need to know how to draw a circle. Anyways, the double angle identities. Let's do it. We have the sine of 2x. Okay, the sine of 2x can be written as the sine of x plus x. And according to our angle addition identity, we can rewrite this as sine of x cosine of x plus the sine of x cosine of x. But this simplifies very nicely. We'll get 2 sine of x cosine of x. And that's it. There's nothing else to do. That's the only version we have of the double angle identity for sine. Now let's go over cosine. The cosine of 2x, with a very similar strategy, can be written as cosine of x times the cosine of x. I don't know what happened there. Minus sine of x times sine of x. Okay, here we have cosine x, that will be cosine square x. And here we'll have sine square x. And that is the first identity for cosine 2x. We have 2 more. Now these 2 other identities follow from the Pythagorean identity by replacing cosine square and sine square respectively. We have cosine of 2x, and we're going to replace cosine square by 1 minus sine square. Let's see that happening here. The sine square plus cosine square will be 1. We can rearrange to solve for cosine and get cosine is equal to 1 minus sine. And we're just going to replace that over here. So that'll be 1 minus sine square minus sine square. And that'll be 1 minus 2 sine square. That is the second cosine double angle identity. The final one will be cosine of 2x is equal to, this time I'm going to replace sine square of x by 1 minus cosine square x. That'll be cosine square x minus 1 minus sine, or minus cosine. That'll be cosine square x. Cosine and cosine add up, minus 1. And here we have a parallel structure, as you can see, except the sine is negative, and here the cosine is positive. So that's it. We have 1, 2, 3, and 4. God damn it, I forgot the tangent last time, the angle addition identity. We still haven't covered tan of a plus b, and we can cover it very easily. Tan a plus b is just sine a plus b over cosine a plus b. Now we can expand this, which equals sine A cosine B plus sine B cosine of A. All of this over cosine A cosine B, weird B, minus sine A sine B. And now we're going to do something, well, no one thinks of usually. If you want to derive this yourself, you're going to multiply by 1 over cosine A cosine B, meaning in the numerator and in the denominator. Okay, what will we get? We'll have sine A cosine B over this. Well, the cosine B's will cancel out, and we'll be left with sine A over cosine A. Cool. Here we'll cancel out the cosine A, and we'll be left with cosine B. So sine B over cosine B. Over here, cosine A cosine B and its reciprocal will produce a 1. And here we'll have sine A sine B over cosine A cosine B, and I'm gonna distribute it in a very specific way. Well, I'll put the sine A over the cosine A times the sine B over the cosine B. And as you can see here, this is basically tangent. We have sine A cosine A, tangent of A. Sine B cosine B is just tangent of B. We'll have 1 minus tan A, that is ta, but it's fine, times tan B. And that's the identity I forgot. This is emotionally draining. I'm very sorry. But if you want to get the difference one, you could just put a negative sign, and the negative sign will carry over here. You can take it out, and over here you can take it out, and you're basically switching the signs just like we did before. Okay, back on track. Where were we? We proved the double angle identity for sine and for cosine. We're left with tan. We have tan of 2x, and according to the identity I forgot, we'll get tan of x plus tan of x over 1 minus tan x times tan x. Simplifying, these add up to tan x. These multiply 1 minus tan square of x, and that's it. It's as simple as that. We have the double angle identity for tangent. We must push forward, my fellow warriors, and I didn't write the title. 1 sec. There you go. Half angle identities in a half-baked video. Anyways, let's go. So we previously did the double angle identity, and that directly follows. I mean, you don't even have to do anything, since that sort of is a half angle where you have a 2x initially and then you have an x. But this is a little more specific. Let me show you. We have the cosine. We're going to use the cosine of 2x is equal to 1 minus 2 sine squared x. Of course, here we have the half angle. We go from 2x to x, but that's not what we want. We want to go from x over 2 to x. And that can happen very easily by a replacement of x. We can just do, well, x equal h over 2. That way, I could do cosine of 2 times that'll be cosine of h, equals 1 minus 2 sine squared of h over 2. That's essentially it. We're going from h over 2 to h, except we have to solve for sine. That is the whole point of this identity. So first off, I'll multiply by -1. It will make life easier. We'll get negative cosine of h equals -1 plus 2 sine squared of h over 2. And I'll move the 1 to the other side and divide by 2. So we'll get sine squared of h over 2 is equal to 1 minus cosine all over 2. To get rid of the square, we must take the square root. And there we go. But don't forget about the positive and negative, since, well, sine of h over 2 could be negative, but the square root only gives you the positive answers. So you must put positive, negative, square root 1 minus cosine h over 2. And so that's our half angle identity for sine, and the cosine is very, very similar. Okay, so this time we're going to use the 2 cosine square x minus 1 version. And we're going to do the same sort of replacement. We have cosine of h equal to, well, I forgot, no, I didn't forget anything. 2 cosine squared of h over 2 minus 1. And now we're going to solve for cosine square, and we'll get cosine of h over 2 is equal to cosine h plus 1 over 2, all rooted, but do not forget the plus and the minus sign. And that is the half angle identity for cosine. Another tangent one, which is a little more interesting, I have to say, because you get rid of the radicals. And radicals are never nice. I'm not talking politically, but yeah. Anyways, so we have tangent of x over 2. We're using x again. I like x. Tangent of x over 2 will be sine of x over 2 over cosine of x over 2. Now we know that both sine and cosine of x over 2 include a radical. So I'm not going to put two radicals on top of one another. I'm just going to combine them like you can. And we'll get the square root. It was 1 minus cosine of x over 2 all over 1 plus cosine of x over 2. Now, of course, we're dividing these. We can do 1 minus cosine x over 2 multiply the reciprocal. Damn it, that's another chunk. We'll have the square root of 1 minus cosine x over 2. What did I write there? Times 2 over 1 plus cosine x. And that's the reciprocal. The 2's will cancel out. Very nice, very nice. I will have this equal square root of 1 minus cosine x over 1 plus cosine x. And now everything is crooked because this broke. Okay, so I forgot the plus and minus signs that come with it, and so we can add them. But as we'll see, they'll not be important later on. So to simplify, I'm going to multiply by the conjugate of 1 minus cosine, which just happens to be the denominator. So this will be 1 plus cosine x, and here 1 plus cosine x. Of course, 1 minus cosine times 1 plus cosine will give us 1 minus cosine square x over this expression, but now squared since we have two versions of it. Cool. Now if you notice, 1 minus cosine square is just sine square according to our Pythagorean identity. And sine square, square rooted, is sine. And 1 plus cosine square, square rooted, you'll just get 1 plus cosine of x. And the plus and minus sign will not be necessary since we got rid of the radical. And that is the half angle identity for tangent. Before we move on, we do have another identity where we could just multiply by the conjugate once again, but the conjugate of the denominator. What will this give us? Well, this will give us sine of x times 1 minus cosine of x over 1 minus cosine square. Cool. 1 minus cosine square is just sine square, as we keep saying. Let me just write this down. Over sine square x. We have some simplification here. We can cancel one of the signs, and we'll be left with 1 minus cosine x over sine x. And this is the second identity. It's the same here, but the reciprocal with the negative sign, or the conjugate of 1 plus cosine x. Can you believe it? We're almost done. We have product to sum, sum to product, and that's it. And they're very similar, just like the previous two. Okay, product to sum. How do we do this? Well, we can add two of our known identities, namely sine of x plus y. I have no idea why I did this. I'm tired. Sine of x plus y plus sine x minus y, what will this give us? Okay, let's see. This one will give us sine of x cosine of y plus sine of y cosine of x. And we're adding this, which is sine of x cosine of y, identical, but we have minus sine of y cosine of x. Very nice. These cancel, and we're left with two identical terms. We'll add them up into 2 sine x cosine y. Now this is equal to that, so I'll just write it right here. Plus sine of x minus y. Very nice. This is a product and this is a sum. One more thing, divide by 2 on both sides. You get rid of this, get 1 over 2 sine x plus y, well, apply to the whole thing, 1/2 sine x plus y plus sine x minus y. And this is the first product to sum identity. Alright, now we're adding, well, subtracting them instead. We'll get, let's do it mentally. We'll get sine x, sine, see, this is, you know what? Fine, I'll write it. Sine x cosine of y plus sine of x sine of y cosine of x, well, minus sine of x cosine of y minus minus, which is plus sine of y cosine of x. Now these terms cancel out and we're left with 2 sine y, that is not a y, cosine of x is equal to our initial term difference minus sine x minus y. Same thing, divide by 2 on either side, no, on both sides. And there you go. The sine of y cosine x is 1/2 sine x plus y minus sine x minus y. Essentially what we did is switch these arguments around and you can use this. I have chalk all over the floor, purple, white, whatever you want, it's there. Okay, now for the cosine ones. We have the cosine of x plus y plus the cosine of x minus y. What does this equal? Well, this equals cosine of x cosine of y plus sine of x sine of y, well, not plus actually, minus, plus cosine of x cosine of y. Now we have plus sine of x sine of y. Again, these cancel out and we're left with identical terms. So we'll have 2 cosine x equal cosine y, and this equals the initial one, which is cosine, no, I'll put parentheses from now, cosine of x plus y plus cosine of x minus y. Divide by 2 on either side. Again, I said either. Divide by 2 on both sides. And that's it. Cosine x cosine y is half cosine x plus y plus cosine x minus y. One more. As I walk through the valley of the shadow of death, I look at. Okay. Cosine x plus y minus cosine x minus y will get, well, cosine of x, cosine of y, sine of x, again minus sine of y. This time we're gonna do minus this one, cosine of x, cosine of y, minus sine of x, sine of y. If you're wondering why it's minus, well, originally in this it will be a plus, but it gains a minus sign from this. These cancel and we'll get negative 2 sine x sine y is equal to this difference, and that will be the cosine of x plus y minus the cosine of x minus y. And then we'll divide by negative 1 over 2. And again, in some textbooks, we'll see that the negative sign is taken inside and these are switched around. Or you could keep it like this for the sake of staying symmetric, or well, conserving the symmetry with the other identities we did previously. We're almost done. Sum to product. That is it. I'm afraid the quality deteriorated over time, but my back deteriorated over time and my speech too. Anyway, sum to product identities, and they follow again directly from the previous ones. Let's see how that happens. We'll have, as we saw last time, 2 sine of x, cosine of y. If you remember, this is equal to sine x plus y plus sine x minus y. Very nice. I mean, we already have the sum to product. The problem is the angle right here is x plus y, and we want a singular term. How do we do that? Well, easily. We'll do x plus y equal a, and x minus y is equal to b. Alright, so we'll replace the a there and the b there, but these will be in terms of x and y. I want everything to be in terms of a and b. Okay, well, we have a system of equations that we're not going to solve, but we're going to solve for some variables. Adding a and b, a plus b, you get x plus x, 2x, and y minus y, which is 0. 2x is a plus b, so that means x is a plus b over 2. Very nice. Now subtracting them instead, we'll get a minus b is equal to x minus x, 0. Y minus minus y, that's 2y. So y is equal to a minus b over 2. Now replace, that's it. We get sine of a plus sine of b is equal to 2 times the sine of x, which here is a plus b, over 2 times cosine of, cosine of a minus b over 2. And that is 1 out of 3 sum to product identities. Okay, another result last time we achieved 2 sine of y cosine of x is equal to sine of, x plus y minus sine x minus y. Very nice. We'll do the same procedure and we'll get 2 sine of a minus b over 2 cosine of a plus b over 2 is equal to sine of a minus sine of b. And simply, that is our second sum to product identity. Okay, a third result we got last time is that 2 cosine of x cosine of y is equal to, cosine of x plus y plus cosine x minus y. Same exact procedure. We replace the variables. We'll have here a plus b over 2 and a minus b over 2. And we'll have the cosine of a plus the cosine of b. And that is third, 3 out of 4, one more. I need a drum roll, this is happening. No! The thing about this board is it's very fragile. It'll be fine. Onwards, we have the last result. Negative 2 sine of a, or sine of x, I just switched variables midway, at the end, equals cosine of a x plus y minus the cosine of x minus y. The same exact procedure. Negative 2 sine of a plus b over 2 times sine of a minus b over 2 is equal to the cosine of a minus the cosine of b. And that's it. We're done. Personally, I don't use the sum to product, product to sum. They might be useful in some questions, maybe a couple of Olympiad or competition questions. But that's it. I believe these are 32 in total. I hope they're all comprehensible. Is that what? Yeah, I think that's the word. Nothing is comprehensible to me anymore. I hope you enjoyed. See you later.